I'll go ahead and start introducing our next speaker. So Dr. Daniele Tonina is a professor in the Department of Civil and Environmental Engineering at the University of Idaho and serves as co-director for the Center for Ecohydraulics Research. I will summarize some of his bio and omit more because it's lengthy and he's a very busy man. So Dr. Tonina joined the Center for Ecohydraulics Research in 2009. Natural environments are complex systems that require a holistic approach for synthesizing physical and biological processes. He follows this approach in his research, which can be broadly defined as ecohydrology. His research interests are in identifying and modeling linkages between physical processes and biological systems. This line of research improves our knowledge and ability to manage and protect river basins, water supplies, and riverine ecosystems, and thus forms an important basis for new public policy, urban development, and engineering designs. His research is not focused on one subject, but it examines the connection and interaction of different components that form a natural system. And he's going to be speaking to us about nitrification and denitrification, temperature, dissolved oxygen changes within the hyporheic zone, and emissions of greenhouse gases. So with that, let's welcome Dr. Tonina.
Thank you. So first of all, thank you for having me here. I truly enjoyed these last days and hearing all the work that has been done here in the Trinity River and all the science that is coming up. And I learned a lot. And so far, we have been hearing about surface water, how surface water impact temperature, growth of different type of organism. And now what I would like to do is to change the perspective and looking at how surface water impact not just how surface water moves in the streams, but also how surface water enter the stream bed. And stream bed are important ecosystems where even fish use them to evolve, like salmonid laid eggs into the stream bed. And so during that stage of life, they depend on this surface flow that move into the pores of the stream bed. And there are a couple of things that I would like to address today and convey to you. One is the fact that this connection between surface water and the subsurface water not only depend on the characteristic of the stream bed, so its permeability, how also the permeability changes spatially, but it depends on the river morphology and the hydrology. So these two effects impact how much water then move into the stream bed. And this system is complex and is changed locally, but if we underline the main mechanism, then we are able to scale process that occurs at the small scale, at the continental scale. And the work that I'm presenting is done by not just me, by a lot of other people, and involve not just engineering, morphology, but hydrology and biogeochemistry. Okay, So, and the concept is that finding scaling, we can move from what happened here at this local scale that is important for all the microorganisms that lives both on the benthic area, but also into the stream bed. Remember that fauna can move from the top to the bottom, can burrow into the stream bed, and salmon lay the eggs. But as the water moves through this stream bed, because a biofilm grows around it, reactive solute can be changed, so they go through transformations. And so as the water moves through the sediment, the one that comes out has a chemical and physical signature that is different from the surface water. So the stream bed works as a filter, like a water treatment plant in a certain way, and also as a cooling effect or a warming effect. So water that might be warm at this point here, as it goes through the sediment, absorb that heat, and then the cooled water that enter during the night can be warm up. So the water that exits has a temperature, chemical, and other characteristics that is different, that can then sum up as you move through the systems and have actually an impact at the global scale. And to show this impact, what I decided to present to you is how rivers can also emit greenhouse gases. So first of all, what is a hyporheic? And hyporheic evolved as a concept along the last 30, 40 years. At the beginning, the concept was just surface water that mix with the groundwater, to come up to be a concept that is actually mainly surface water that enter the stream bed and then exit. There is some mixing that occurs, but in a steady state concept, that the mixing is very low. So what will actually happen is that the surface water as I enter is a chemical signature is different, so it gets closer to what the groundwater is, but it's mainly surface water to move it. And here I wanted to show this one with this movie, where water is moving from right, so from here, it's dune systems, so going from here to here. These one are blob of dye that we injected, and what the movie should show you is that this, this move. Notice the time down here. So the time scale of this process is very different than the time scale of the surface water, and because of that, reaction rate has a certain impact of what is happening. So after 24 hours, 26. Some of the dye exited. So typically in a dune, we have the downwelling on the upstream side and then downwelling on the other side. And notice that the water surface is almost flat, and this pushing is due to pressure difference that occurs. So the velocity basically accelerates over here, so the pressure becomes higher in this area, and push the surface water into the sediment. Here we typically have recirculation eddy with low pressure forming. So not only changing water surface elevation, but changing in a velocity field generated this flux. And this process is ubiquitous along the river network, and the reason behind that one is because stream beds are made of a permeable material. So unless we are dealing with bedrock, but even in bedrock, there are fissures inside that surface water can penetrate and eventually get out. And there are several mechanisms that it brings in. Here in this cartoon, we can see the river that goes from unconfined to confined, with change in lateral, but also bedrock processes, change in water surface elevations that can be an indication of changing in head of energy that push there. And then we have sediment transport, change in turbulence, and also change in the permeability of the streams. And because all of these processes occur a different length scale, hyporheic occurs at a different lengths. So we have different residence times, different path length. Here in this cartoon, we show that the micro roughness, like large pebbles, boulders, but also cluster of sediment can generate very shallow hyporheic that is superimposed to the one that might be generated by, let's say, pool to pools. Notice that in doing that, when we go with something that lasts probably a few minutes to something that may last a few hours, if not several months. So here it could be hyporheic at the channel reach scale, which will have residence times that can be months. So we start to have a different type of time scale. Something that happen on the river can be, so the flow might take only a few hours to move from upstream to downstreams, but here in the hyporheic it can take a month. And in certain cases, like at the valley scale, we are dealing with water that reside there for years. So there is a lot of process that can occur and can be accommodated by the range of resident times that are present there. And here what I would like to show to you is the different mechanisms that can create that hyporheic. And the way that was schematized was to suppose to have a small control volume. The lower part get down to the bedrock area, so is permeable. The side of this control volume are parallel to the general flow, so we don't have a flow that enter on the side, such that the groundwater move from upstream to downstreams. Meanwhile, the upper part of this control volume is lay on the stream bed, so the water sediment interface, such that the change in discharge between upstream and downstream from these control volumes and the exchange that drives the change in volume that is present there. If we assume that we are in a steady state conditions, then this part can be simplified. And so what we can highlight is how the exchange is generated by the change in discharge as you enter into the control volume through the groundwater. We can move from the discharge, so here we have a difference, then we can make it very, very small and go to a differential where Q can be represented as a Darcian flux. And as a Darcian flux, what it tells us is that the flow in the groundwater depends on the permeability of the sediment, the change in head, and the area of our control volumes. The beauty of this one is that then we can break it down, so we can derive, we bring this one in, we substitute Q, and we have these three terms that can be derived separately. And that allows us now to see three mechanisms that can drive hyporheic. So the first one is the change in head. So the change in energy between two places, let's say upstreams and downstreams, these riffles can drive hyporheics. And I wanted to highlight two different mechanisms that are important for us. One is the fact that if we are looking at the rivers and we look at the riffles or boulders, we can see that there is a change in water surface elevations. And water surface elevation can be seen as a head that moves surface water, but also groundwater into the stream bed. But then there is another one that can occur. So here is an example with a rod or a stem of a vegetation, which has a very limited impact on the water surface elevations. But what it does is change the dynamic pressure. So velocity gets toward the vegetation stems, it becomes very, very low. So we have an increase in pressure. Downstreams, we create a recirculation eddy that increase the pressure. So hyporheic is driven into the sediment. And this is due to dynamic head. Meanwhile, in pool and riffles, most is driven by change in water surface elevation upstream and downstreams. Then we have the change in alluvial depth. So as we have a bedrock or change in the stream bed, we can have this other mechanism that is there, even though we have the same head, but also change in not channel width, but valley width. So confinement can create this area of upwelling and downwelling. An important part that in the past was a little bit overlooked is the fact that, especially in gravel bed river, we have a change in permeability. We have area where we have gravel, fine gravels, area with a lot of fine inside, and those change in permeability because through maybe this layer of clay, there is a less flow that can move. Some of it needs to get out of the stream bed, and then if the permeability gets larger and larger, we can have this movement of a flow again into the sediment. So contrast in permeability can generate this upwelling, the welling mechanism. So differences in a grain size distribution is important to generate this. And then there are two other mechanisms that can not to be studied in a steady state environment. One is the erosion and deposition. So when we have scour, we have also upwelling of water that was trapped into the sediment. The sediment porosity typically goes between 28 to 40%. So there is a lot of water that is stored inside, can be released, but at the same time, as we deposited sediment, some of that surface water is stored inside that one. And when the sediment are the pores are very large, also turbulence can actually penetrate into the stream bed. And to give you an idea, this turbulence mixing can go when we have a lot of sediment and fine sediment can be related only in the first 2d50 of the stream bed. So the median grain size, but when the gravel is very clean, turbulence can penetrate down almost 10 times the median grain size. So it can be a substantial depth into the stream bed. And this mechanism are present also with vegetation. I already showed that concept, and here is shown in some experiment that we have done in Boise, where flow basically hits. It is a numerical simulation support the measurement that we have done, that we have it is a low pressure that generate hyporheic, and this one is mainly due to this change in velocity, upstreams and downstreams of the stem. This is the same mechanism basically that salmonid use. The salmonids created these depressions into the stream bed that looks like a dune, and the eggs is in this area here, and which focus most of the surface water that enter the stream bed. This process is extremely important because eggs for their development needs oxygen, and the oxygen to get to the eggs is advectively transported by the hyporheic flows. So if we turn down that hyporheic, the eggs basically suffocate. And that is one of the mechanisms to mortality of the eggs is the impact of hyporheic characteristics. So if the flow is too low or the surface water is too warm, then the metabolism of the eggs are very active, so they don't have enough oxygen surrounding to be able to develop properly. And to study this effect, one can recreate the dunes in the laboratory. In this case, we are using a type of a material that is called a THV that becomes transparent when it's immersed into a fluid that has a 14% of Epsom salt. So here is in air, and then when we add the fluid, they become fully transparent, and that allows us to measure how the flow enter the stream bed. I wanted to show you a couple of a movie. This one is, we have the dye over here that is injected on the upstream side of the red. And in this case, without a pocket. So surface water moves in, it does this arch flow, similar to what we notice in dunes. But then I wanted to show you what happened once we recreate an egg's pocket into the stream bed. So this flow is in the same dune stem characteristics, same flow. The only difference that we created a pocket of very large particles that should mimic the egg pocket of the reds. And here is the dye, here is the eggs pocket, and the high permeability and the larger pores make the flow going into the eggs. And notice how dispersed that happen and how different the flow in the upper part is basically laminar. Inside the egg pocket start to be closer to turbulence or in transitional flow. Here, another movie that it goes directly into the egg pocket. And I think here you can see even more. Look at how the flow moves and almost undulate, like what we would see in the surface. So hyporheic is extremely important to make sure that the eggs get the right amount of dissolved oxygen around them. And the structure of the reds with the surface water impact how much flow gets there. And here I wanted to tie it back to surface control and the shape of the reds. These graphs are dimensionless graphs. We have the Reynolds number, which indicate how strong is the flow in the surface related to the viscosity of the flow. Meanwhile, here is the Froude number, which related the inertial forces with the gravitational forces. And for us, we can see that both of them as related to how strong is the flow in the surface. So the larger is the Froude number, or the larger is the Reynolds number, the stronger is the flow. So in the same river, for the same characteristic of the reds, we can see it as an increase of discharge. And here we have the downwelling flux. And what is happening is that as we increase the discharge in a river, we also increase how much downwelling flow gets into the red. And that is similar if we have a very small red, and in this case, a red that has length of about meter in here. We go with the Sinuk, so almost a 3 meter long. And in all cases, we have the same trend. What is happening is that the smaller is the red, and typically the larger is the wavelength. And the ratio between the amplitude and the wavelength, the stronger is those downwelling fluxes. So there is this connection with surface hydraulics and how much downwelling occurs. There is also another important effect that we need to consider, which is how strong is the groundwater, because locally we could have groundwater that goes up and it can reduce so how much hyporheic can be formed. But those one we can account for them in this equation here. We have the downwelling flux, and this groundwater is basically the velocity that could have been gaining reaches, so the upwelling of groundwater into the streams, or in losing reaches, groundwater is basically taking away water in that one, and that impact the characteristics, how much discharge can go into the eggs pocket. What I wanted to highlight is that here is the ratio between the downwelling velocity and the velocity into the streams. And here is the dimensionless depth of water. So it's the water depth divided by the height of the dunes. And in this case, let's have a static dunes. So typically the dunes are dynamic. The larger is the flow, the larger is the dunes. In this case, I wanted to keep it the same and see what is the relationship by increasing the discharge. And what is happening is that as we increase the discharge, so the depth is getting larger and larger, we have an increase of the downwelling flow into the sediment. Notice that the amount of flow that goes into the hyporheic is very small compared to what is in the river. So is less than 1% in most of the cases. And that impact also how long the flow remain into the streambed, and in this case, increasing the groundwater upwelling or downwelling, we have this a decrease of how long the flow stays into the streambed, and that is important for biogeochemical reactions. Similarly, we can do this type of analysis not on dune, but also in pool and riffles, which is typically the most common type of bed forms in gravel bed rivers. Here, the model looks at the alternate bar that can be formed and how the alternate bar geometry is impacted by the surface hydraulics and the sediment that is present there. Here we did the exercise by changing the slope by less than 0.5% to 3%, and that impact how the flow gets into the streambed. Typically, the steeper is the stream, the more shallow the flow, the hyporheic flow get into the streambed. And here to highlight how the processes occurs, I wanted to present the same graphs as before, where we do have the downwelling velocity normalized by the surface velocity. And what I wanted to show here is the fact that as we increase the discharge, in the pool and riffles, we have the opposite characteristics. For dune and for red, we have this increase. Instead, in the pool and riffles, we have a decrease of the flux that get into the streambed. And that is due to the different mechanisms. So in dune and red, mostly is the dynamic head that drives that process. In pool and riffles, is the difference in water surface elevations upstream and downstreams of the riffles. The other part that is interesting to notice is the impact of roughness. So DS is the ratio between the median grain size and the depth of water. So it tells us how rough the streambed is. So this value here is 10 times rougher than this one. And the surface roughness has an impact on how much hyporheic gets there. So for the same pool and riffle systems, so let's go in this system here with the same surface hydraulics, the fact that this pool and riffle has a rougher surface is driving more flow into the stream bed. Again, notice that the exchange is very small. So we have order of a magnitude less flow to move into the stream bed. And the impact that happen is also how long it stays there. So as the discharge gets larger, so we can see this one, or as a surrogate for discharge, we have that surface discharge. We have that the resident times get longer and longer into the stream bed. So why I wanted to go all three is because I wanted to make sure that there is this connection between surface water and subsurface and hyporheic. And we have tools that we can then connect those discharge and how long they stays there with surface hydraulics. And those impact not just how much water moves between the river and the subsurface, but impact also the biogeochemistry, water quality, and the quality of the habitat. And I want to drive through those one in the next part of the talk. So here is a set of experiments that was designed to actually understand how is hyporheic impacting the biogeochemistry in the stream bed and in the surface. We have 3 replicates, so there are 3 flumelet here, one in the center, and the other one, they were full with sand, where we recreated dunes. Each of them were independent to each other. The only thing that they were sharing is the same surface hydraulic. The surface water was exactly the same. They have the same grain size distribution, the same geometry, we inoculated the same sand, such that the difference between the 3 of them that will provide us the natural variability on how the biology grew into the stream bed. We highly intensified the measurement. Here is a set of optical cables that were embedded into the stream bed in 232 locations. So we were able to measure the dissolved oxygen concentration in those locations without having to extract water, which may impact the chemistry of it, because it impacts how wide is the volume of water that we extract. And then we also have a number of 32 locations where we extract water to measure nitrate and N2O, and to also make analysis on the type of organism that were living in the stream bed. And here is the result that we got out of that. So the first part is a dissolved oxygen. So here is the dune, surface water, and so the black line here shows you the flow lines generated by hyporheic. The one at the bottom is basically tell us that is horizontal flow that was mimicking groundwater. Here is the flow that enter and exits the systems, and the upper portion of the dune is in oxy condition. So dissolved oxygen is very similar to the one on the rivers, but as it goes and stay longer into the stream bed, we start to have this exponential decay. And this exponential decay gets faster as the dune gets smaller. So here is the length of 2 different dunes. Similarly is a nitrate. As a nitrate was changing to the dune, we have a reduction of a nitrate that occurs into the stream bed, and that was a function of, again, of the resident times. The other part that is interesting is the formation of nitrous oxide, which is an important greenhouse gas, and we noticed that there was a formation of that into the stream bed. So we have this area of high productions, and in certain cases, then removal of N2O, since it's not a stable and is not an end product of denitrifications. What is interesting is not just a specialization of the chemistry, but also specialization of the organisms that are there. So here is the NOS-Z is a gene that was present in certain microbial community that were present there, and is very important to finalize the denitrification process. And what is important to note is that the location of organisms that have these genes is exactly superimposed and correlate where N2O is a maximum peak. So the surface flow impacting the biogeochemistry impacted also how microorganisms changed their characteristic into the stream bed. And here I wanted to tied to this concept of a flux. So how much of that water with that characteristics enter the stream bed? And this one is a very similar concept of the one of the drift that John showed to us in the first days, where it not only depends on the concentration, but also it depends on the flux, on the velocity of the flow. And similarly in here, what we can see is that here is for all flow lines, we mapped what was the concentration of N2O into the hyporheic. And what is interesting is that we maximize that when in the anoxic conditions, when the dimension time, so here is the resident time, so normalized by the resident times by denitrifications, or the product between the times and the reaction rate for denitrifications. When we are in anoxic conditions, we maximize the productions, but that doesn't quite match where N2O, the maximum load of N2O comes out. That is, so this area here tells us the concentration of the flux, where it goes in. And we notice that that's happened in this area here. Meanwhile, where we are close to the crest of the reef faults, we are the dune, sorry, we have almost zero emissions. When we are in the longest part here, we have almost a removal of greenhouse gas. And that led us to looking at the systems in this fashion, where the flow lines are too short, we have no productions, where the flow lines are too long, we have consumptions, or if they go to the end, is a very low velocity, so the loads are very low. So only in this area here that are on the borderline to be oxic and anoxic, we have enough production, but enough velocity to bring N2O out of the stream bed. So the presence of hyporheic and its characteristics can be a sink or a source of greenhouse gases from streams. And here is where we can start to build models to be able to explain this mechanism. So the first part is to be able to understand the hydraulics. So like in a rivers, to be able to understand how fish use the environment, we need to characterize what is the velocity, what is the depth. And it's in same fashion, we need to characterize the velocity and how the hyporheic moves into the stream bed. Then we can then characterize the resident times. We can see how temperature change. And this is quite interesting because we have daily variation in the surface water, and we have that remnant also in the hyporheic. This is a cut through it. This area is downwelling. Then we have cold water. We have still warm water. And this warm water is the previous date that is still migrating into the stream bed. So the same variation in temperature that we see in the surface water then can be mimicked into the stream bed depending on the resident times. And these temperature are very important to be able to track because the reaction rate into the stream bed are temperature dependent. And once we do have how long they stays, what is the characteristics in terms of temperature, then we can map how, for instance, nitrate change into the stream bed. And at this point, this one is a numerical modeling, and one of the questions is how well does it work when we compare it on rivers and their behaviors. So here is a set of analysis that we have done in Bear Valley Creek in Central Idaho. Here is a reef fall pool systems. We instrumented that one with a temperature profiler. So these temperature stakes get into the stream bed. The upper sensor is a temperature sensor, is a T-bit that stays in the rivers. The other three are in the stream bed, 15, 30, and 50 centimeters below the stream bed, and we're located in these locations. By looking at how the temperature change at different depths, we can measure and predict what is the flux, the interstitial flux. So we can determine if in this location, so where there is a black dot is one of those stakes. This one here is blue color, it means that it was upwelling. The red color means that it's downwelling. Meanwhile, the shaded orange and blue is the numerical model. So the measurement give us a localized point. The numerical model provide us the entire stream bed where we have upwelling, downwelling. And what is interesting is that we were able to match what in the field we were seeing, and also in this point here where it was at the borderline number 2, we were also the model was telling us that we are a transition between upwelling and downwelling. We can then look at how well we can measure the change in temperature into the stream bed. So this one is the index of agreement between temperature measured and predicted at 2 depth into the stream bed, and we get a very good job in predicting those one once we have a very well defined and confined numerical model. How well we can predict the reaction rate. So we use the data provided by Bollier et al., where they measured nitrous oxide production in this set of reaches in the Kalamazoo rivers. And we were able to recreate our model because they made very accurate measurement of boundary conditions of surface water, what type of grain size were there, what type of bed forms were there. So we were able to reconstruct the numerical model, and our model are the blue circles, meanwhile the measurement are at these triangles. And in most cases, we were able to recreate the emissions of nitrous oxide from the stream bed. So this model may work very nicely when we characterize properly the systems. However, what happens if we want to go at the larger scale? Because if we work at the smaller scale, those productions may not be that important, but they start to be important, especially in water quality, when we start to look at the integral impact of hyporheic along an entire river networks. So when we wanted to move from something that is very local to something that is at the watershed scale, we needed to start scaling those processes. We have seen that the hyporheic is quite complex. It depends on local characteristics, how we can upscale those one. And the idea behind that one was proposed by Ocampos and is looking at the ratio between time scales. So the way that they suggested to work is to characterize what is the advective times. So how long hydraulically stays the water in a certain compartment, and how fast is that biogeochemical reaction occurs. So the way that we implemented that idea was to use the median resident times into the stream bed, normalized by the reaction rate that we are looking at. So if we were looking at the dissolved oxygen, so normalized by aerobic respiration. So if we are looking at nitrification, the product nitrification rate, or denitrifications, if we are looking at nitrous oxide productions. And that is for the hyporheic. What happened instead on the streams? What would be the right scaling factor that can tell us how long is those particles be impacted by reaction to the stream bed? And the way that we approach that one is to use the mixing, the vertical mixing, which is driven by turbulence, and that tell us how much solute can move between the surface and the stream bed, and so can feel all the different microorganisms that are in suspension into the stream bed. So we have this idea to use resident times as a scaling factor, and what we did is then see what model are available. So for dunes, there is this model that link resident times with the characteristics of the morphology and the hydraulics of the dunes. And then there is another work that was done linking the resident times with the morphology of pool and refill systems. The last ingredient is the timescale of the reaction rate. And this one was collected using the denitrification velocity proposed by Mulholland and Bolke, and is a function of the size of the rivers. So now we have the ingredient for both timescales. And what we did was to use the links to experiment, where we're collecting throughout the entire United States in different biomes, different climate conditions, different type of river. So from plains to gravel bed rivers, to mountain rivers, tropical systems. So different river with different characteristics and in different locations. So some were in agricultural land, in a reference that for them were natural streams and urban streams. And here we decided to normalize the flux of nitrous oxide by the flux of the reactant, so nitrate and ammonium multiplied by the stream velocity. So how much it gets into that particular reach and from what instead is emitted out of the stream bed. So we have it as a dimensionless flux. And when we put the dimensionless flux in this dimensionless framework, where here is the Dam Kohler number, which is the ratio between the median residence time in the hyporheic normalized by the reaction rate, all of them stays on the same lines and provide us a scaling law in a certain way that we can look at. So a river that has these characteristics may have that much emission that occurs there. The important part here of the analysis, even though we see all this scatter, if we look at if these three environments are statistically different, the analysis tell us that they are not. So all of them can be used once they are dimensionalized to characterize this flow. The next step that we have done was to separate also what is happening on the benthic area to what happened into the hyporheic. So the links to models were able to separate and disentangle the nitrous oxide production between the benthic and the subsurface. And that's what these two lines provide us. So the gray black line on the surface is a productions by combining hyporheic and benthic. Meanwhile, the lower one is just the benthic flow. And what we proposed then was to use this way to interpret the data, where small streams were depend mostly on hyporheic. Meanwhile, large rivers will be mostly dependent on a process that occurs on the surface, because what we have seen is that as the flow increases, typically hyporheic becomes a small amount of the flow that is interacted with them. Once we have this idea and those two lines, what we wanted was to see, are those two lines true everywhere in the world? And so we collected from the literature data that others collect in Africa, in other parts of the United States, and along the Mississippi River, to see if those relationships hold. And here is basically our models with what was observed, and the model basically used those two equations plus an equation for surface water, and comparing them with more than 400 measurements collected by others. The model works quite well in predicting those relationships. And what this one shows is, in a certain way, this is the dimensional flux of nitrous oxide, which is very high in small streams. Then it becomes lower in intermediate streams, and then when we are in large streams, it starts to pick up again. What this one can be break down tell us is that the hyporheic is very important in small streams. In large streams, instead, is surface water that becomes important. With this framework, we can now, and all of the uncertainty associated with that, and we can now see how hyporheic and surface water are important on the local scale, not just on the local scale, but the continental scale. The other point that I want to point out is this one. The red circle are measured value, the square are the model. So this is not error. This is a natural variability for a given width of a channel. Both trends are very similar. So if we do the regressions through the measured data and regression through our model, they are pretty much match and they have the same shape. What also shows is that as we move from hyporheic to surface water and the benthic area becomes important, certain processes become less effective. Having tied what happened in the hyporheic with the morphology of the rivers allow us now to move from local processes to the reach scale, and then breaking down the river network in reaches and then integrated at the watershed scale. We can now upgrade or upscale what happened through the continental, not just to the continental, but to the globe. And that's basically this work. What it shows is that if we move up knowing the distribution of concentration around the globes of the reactant, so nitrate and ammonium, the discharge distributions, information of grain size, then we can characterize the dam colors numbers. Through the dam color numbers, those scaling law, we can then determine the global variation of the fluxes, and that then allow us not only to sum and integrate, but also go back and see where are those fluxes stronger, where are weaker, and what are the local processes that make that happen. The other two parts that I wanted to highlight is that we need to make good guess of the permeability of the stream bed, and the way that we have done was to link that one with the median grain size, and the median grain size was driven by morphological characteristics. So looking at the shear stress and how the shear stress can mobilize a median grain size. And that allows us now to integrate, see what are the emissions. So this one is the emission at the annual scale that our model was predicting, that is close but refines what others have done by regression analysis. But the interesting part is that now we can tell which rivers can be the source of it, and also which portion of the rivers. And what was striking for us is that almost 50% of the emission comes from hyporheic processes, so are from streams that are very small, less than 10 meter width. And those one, if we are looking at the surface area, there are only 13%. So small streams, even though the length might be a lot more, but they are very narrow. So the surface is very small compared to all of the other one. They are the ones that contributed the most. So we can look at where processes occurs. And to close up, what I wanted to highlight is the importance to look not just at surface water, but also how surface water and the morphology impact hyporheic fluxes and the interaction with the aquifer, and to look at it in a way that we can scale it. And right now I show scaling that was mostly in terms of morphology, but we needed to think also in a dynamic, using just the mean annual flow. However, because all these processes are non-linear, that means that if we break it down through an hydrograph, so we can have a different result than just working with the mean. So understanding how the hydrographs change over time and how impact, so the depth of penetration of the hyporheic into the stream bed can impact how nutrients get into the stream bed, how then they get mixed and pass on in the next year and sometimes month, because some flow lines are extremely long. Thanks. Excellent.
Okay, thank you. Great talk. So what I'm wondering about is you showed that residence time is affected by porosity, by permeability of the substrate. And a lot of these managed rivers, you know, we don't get any gravel from upstream of the dam or any sediment from upstream of the dam. So we add gravel, but we often don't add fine sediment. And my question is, you know, I guess basically, can the substrate be too clean? And would you ever recommend adding sand to slow down the residence time to have the correct processes or the?
Excellent question. Yes, in a certain way, that could, depending on what is the end goal. If the gravel is extremely clean, then that means that certain processes do not happen. So if it's too fast, it may remain oxic, and so it's not going to provide enough time and enough anaerobic condition to have nitrification, for instance. And so in certain environment, if we have a lot of nitrate, then we don't have that cleaning effect that the streams that may have longer residence times may have. So in certain conditions, the answer is yes. In other, if we want to have a more oxic condition in the stream bed, potentially to have a more habitat for certain fauna, then having a pocket of highly porous systems might be beneficial. And that potentially is the fact that we do have flushing flows. So the hydrographs has high flows that then remove fines at a certain time of the years, and so make those also those sediment, rearranging them, make open up the pores so we can have a more flow that can penetrate deeper into the stream bed and then mix with the one that are below that potentially have a lower porosity.
Thank you.
Thanks.
Thank you. I think I learned more about hyporheic exchange in the last half hour than I have in my whole life. And a lot of the concepts and models that you presented have I think a lot of applicability to the Trinity River. But I just have one question about one aspect of your presentation, and that was hyporheic flow through REDS and its relation to dissolved oxygen and what drives that hyporheic exchange. And some of those factors we have limited direct control over, except one, and that's velocity through dam releases. As you're probably aware, spring Chinook start spawning in September and continue through October. And I think it's reasonable that they likely select red location based on hyporheic flow. And then typically we drop dam releases at a time when tributary accretion is minimal. So river flows are very driven by dam releases. And October 15th, we generally drop at 50% from 450 to 300. Do you think that is influential potentially in egg survival and development and something that we should be looking into or concerned about? We have very little information on egg survival. We're just kind of getting into that in this program with some preliminary data, but it's kind of an unknown for us right now.
That's another important question. So there are a couple of parameter that impact the egg survival. One is the velocity, so the interstitial velocity, and the other one is also dissolved oxygen and the temperature. So the amount of dissolved oxygen that is transported into the surface water is depending on how cold the surface water is. So the colder it is, the more higher is the concentration, because the saturation the amount that can be dissolved is higher, but also depends on the reaction rate inside the eggs. Basically, development, they develop slower when the temperature is colder, so they need basically less oxygen. So the flow could be a little bit lower if the temperature are lower. So it's a balance between the temperature of the water and a flux in a certain way. If the interstitial flow are fast enough, there is then a threshold. When they are too fast, then there is no longer an impact on how the eggs develops. So, and that depends on the surface characteristics, where the reds are located, a little bit their shapes, and the permeability of the stream bed. So if the red is highly permeable, then potentially even a lower discharge or a lower velocity may bring the same amount than higher if the permeability is lower. So it becomes a little bit more site specific. Yeah.
Gotcha. Thank you.
Thanks.